We've been solving systems of equations. Depending on how many variables and how many equations there are in our set, we will get what's called an n-tuple as our solution. So what we're going to do today is introduce a new notation. Take this n-tuple, we're going to write it as a column, x1, x2, all the way down to xn. And we are going to call it x with an arrow on the top. Now, if you read a textbook in print, that's usually in bold font. So this is what's going to be known as a vector. So a vector for us is just going to be a column of real numbers. And the notation we will use is x is an element of what's called Rn. So it's the set of all these columns with n entries. Now, each one of these entries is a real number. Now, in physics, you talk about vectors as something with a magnitude and a direction. And in physics, you use vectors to describe things like force. It becomes much more of a geometric interpretation. Now, in physics, you typically talk about what are called free vectors. These vectors are all the same. You could slide it around, but for us, our vectors are going to be bound. And I'll explain what that means in just a moment. We're going to define some operations as well as a geometric meaning and then connect them. The geometric meaning comes about from interpreting vectors in coordinate systems. You can think of vectors as coordinates of a point. And in 2 dimensions, if your vector kind of looks like this, x1, x2, we're going to take this to be the x1 axis, the x2 axis, and then you can think of your vector as the coordinates of this point. You could also then think of it as an arrow pointing from the origin, which we're going to denote by the 0 vector, up to that point x. And so a moment ago when I said that our vectors are bound, they're always going to be starting at the origin. So it will initiate from the origin and terminate at this point x. You are completely allowed and encouraged to interpret vectors as either points or arrows. Now, here are the main operations that we are going to use. Number 1, addition. So if I've got a vector, let's say it has n components, and I've got another one, the only way that it makes sense for me to add 2 vectors is if they have the same number of entries, and I'm going to define vector addition just by adding them entry by entry. And then we're going to talk about another really important operation that's called scalar multiplication. You can think of it as scaling. Scaling is kind of like stretching. So if I were to take a vector and then multiply it by some constant c, and by our definition, we are going to say that that scalar is going to multiply every entry in that column. Once we've got all of this, then it becomes pretty straightforward to compute things in an algebraic sense. So if U is the column 1, 2, 3, and V is the column 0, 1, 0, each of these vectors lives in what's called R3, the set of all vectors that have 3 components. If I ask you to compute 5u minus 2v, we can start using the definitions that we did above. That's just what it means in terms of symbols. The first thing that I'm going to do is this scalar multiplication, and that means these values are going to go inside. So I'll have 5, 10, 15. Now with the -2, if we're going to follow our definition, there's a hidden plus sign in here. We'll get 0, -2, and 0. And then by definition of vector addition, this will simply be 5, 8, and 15. Now, from these definitions, you can show these other properties are true. So for instance, it doesn't matter the order in which you add 2 vectors. If you want to flip-flop the 2, it's the same result. If you're adding several of them, it doesn't matter the order in which you add them. You will always get the same result at the end of the day. We are going to take the vector 0 to be just the column that holds as many zeros as you need. And so it's pretty sensible that adding 0 to your vector should just keep it as your vector. If you were to add the opposite of a vector to itself, you'll get 0. And then you get all these other boring properties. I'm really just rushing through these because these are all properties that you know from real numbers, and they all end up applying to vectors anyways. With this, you get all these wonderful properties, and again, you'll take them all for granted, but they all work out. So you can make a geometric interpretation of scalar multiplication and addition. So scalar multiplication For example, if I had u as the vector 1, 2, I can draw this. There's a u. If I were to take 2u, for example, that means I'm scaling each entry of the vector, and I'll get 2, 4. So 2u ends up being this vector over here. You can think of it as just the dot. You can think of it as an arrow. So that's what u is. That's what 2u is. You can see that it's stretched by a factor of 2. If I were to do something like negative u, I'll have negative 1, negative 2. This is where my vector u is, and negative u ends up being down here. And so what happens is that putting a negative sign in the front just flips the direction. So if I keep considering all multiples of u, I end up getting a nice little picture. So if u lives up here, u is really just a dot. I found from earlier from the definition that I'd get a 2u here. 3u would live 3 times as far. 4u would live up there, and the same thing would happen down here. Negative u, negative 2u. Now, I just chose to pick these discrete jumps. 1, 2, 3, negative 1, negative 2, negative 3, but I could have picked any multiple I wanted, anything in between. So it turns out there are uncountably many points in between the origin up to there, uncountably many points up to here, uncountably many points all the way over there. And you can see that this just keeps going. If I were to write tu, where t is some real number, this has a geometric interpretation. This is a line that goes through the origin, and it's in the direction of the vector u. Scalar multiples just stretch a vector, and if you take all of them, you end up getting this collection of points. All the dots in blue are the line itself. It's the collection of every single multiple. Now, if I were to do addition, so if I were to say that u is, again, 1, 1, v is 2, 1, so u plus v, as we know, it's going to be 1 plus 2, 1 plus 1, I'll get 3 and 2. So I'm not just interested in the final answer, but I want a way to get to that final result by doing something geometric. So here's the vector u, here's the vector v. I have to end up getting to 3 and 2. So I have to end up getting to here. So what you're going to notice is that if I were to draw a parallelogram where that dotted green line is in the same direction as that solid green line, and if I were to draw a dotted line that's in the same direction as that u, I end up getting something called a parallelogram rule. And that's a way that you can geometrically add 2 vectors. So if I have my 2 vectors, u and v, then I'll just draw a parallelogram, and then the result, u plus v, will be along that diagonal. I now have a geometric way of adding vectors as well as scaling them.